Hi, students. So last class we saw that parallax is the parent shift of a star with respect to the more distant stars because of the movement of the Earth around the Sun. So a closer star is going to have a bigger shift, and a more distant star would have a smaller shift. Now, this image here is giving you the impression that the parallax shift is always a straight line. That is not the case. In fact, the star traces an ellipse. A line is going to be the case if a star is in the ecliptic. So this is the case for a star in the ecliptic. You have the sun here, the Earth orbiting. Imagine that this is a telescope pointing at the star. This is the motion that you see of the star. In the ecliptic, it's going to trace a line. But now imagine that you are looking at a star at the pole. So now the situation is this: the Earth is orbiting the sun, the telescope is pointing upwards, so you're seeing a circle. You're seeing the star doing a circle. In general, the star is going to trace an ellipse. We call this the parallax ellipse. So let's understand in detail how this ellipse happens. To understand that, to understand the signature of the parallax, we realize first that a star at a random orientation with respect to the ecliptic would be seen at an angle theta from the sun, but at an angle theta prime as seen from the Earth. Let us apply the law of sines to this triangle formed by the Earth, the sun, and the star. You have that this angle here is theta minus theta prime. This is the astronomical unit, the distance from the Earth to the sun. And this is the distance to the star, and this is the angle theta prime. So applying the law of sines, you have sine theta minus theta prime over A is equal to sine theta prime over D. So if you isolate theta minus theta prime, and A over D, the semi-major axis of the Earth divided by the distance to the star, is the definition of the parallax. And because we can also approximate to this angle theta minus theta prime to be very small, you can write that the sine of theta minus theta prime is simply theta minus theta prime. So we have theta minus theta prime is equal to sine theta prime times p. If you solve for theta prime, the angle measured from Earth, where in the sine of theta prime we substitute by sine theta because the angles are similar. So the angle theta prime that is measured from Earth is equal to the angle theta that is measured from the sun, corrected by a small amount p times sine theta. So that's the first lesson that we learn here. The angle that you see a star from Earth compared to the angle that you see the same star seen from the sun, they're almost the same, shifted only by a small amount, which is of the order of the parallax. Now, in what direction is this shift? You can see this from this figure. What you're seeing here is the position of the sun fixed. The Earth is moving around the sun. So this is what we see the sun doing, right? This is our perspective. The sun is doing its orbit in the ecliptic. Likewise, a star is doing the same thing. You have the true position of the star here, and this red dot, it's what we see the star doing. It's a reflection of the motion of the Earth. Now, since the motion is a reflection of Earth's motion around the sun, the shift will always be on the direction of a line that is connecting the true position of the star with the position of the sun. As you see here, you can always trace a line, an arc, with the true position of the star, and the apparent position of the sun in the ecliptic, right? So the shift follows the sun's apparent motion. It is along the line that is connecting the sun and the star. Now, this is important to derive the mathematization of the parallax ellipse. So the star is here. That's the true position of the star in magenta. The star has longitude, ecliptic longitude lambda, and ecliptic latitude beta. Now, due to the parallax, we're going to see these coordinates shifted in the line connecting the star to the sun, along this line connecting the star to the sun. The star is going to have a longitude now shifted by delta lambda and a latitude shifted by delta beta. What we want to do here is find the shifts delta lambda and delta beta. So we can draw from here this spherical triangle with vertices at the ecliptic north pole, the sun, and at the star. So you see here. So this side is 90 minus beta. This side is 90 because it's going from the ecliptic to the pole. And this side here is theta, the angle connecting the sun to the star. This angle here is the longitude of the sun minus the longitude of the star. X is the position of the star, and X prime is the shifted position of the star. So the segment X prime is the parallactic shift, which we found to be P sine theta. So we know the position of the star is lambda and beta, X. The shifted position due to parallax is X prime equal to lambda plus delta lambda and beta plus delta beta. And we know that the segment X prime is equal to P sine theta. Question is, what is delta lambda and what is delta beta? So for that, let us define the point U, which is shown here, which will do a plane triangle, a plane straight triangle. And this is a plane triangle because the parallax shift is very small. Now, because of this side, the UX prime came from the pole to the star and delta U, this is along a line of latitude. So the side UX prime is delta beta. The side XU is the difference in longitude, but multiplied by the cosine of beta. That's because this shift here is going to be smaller and smaller as you get closer to the pole. At the pole, there is no difference in position if you change longitude. The longitude is not defined. So at the pole, the shift would be equal to 0. The pole has latitude 90, so it has to be the cosine here that you are multiplying, not the sine. So this is equal to delta lambda times cosine beta. So let's define the angle psi, which is the angle with vertex on x. This is this angle here, the psi. So x is the hypotenuse, call it little a. Therefore, xu, which is equal to delta lambda cosine beta, is equal to a times the cosine of psi. And x prime u, which is equal to delta beta, is equal to a times sine of phi. But you know that a, this shift, is equal to p sine theta. So you have here the relations. Delta lambda cosine beta is equal to p sine theta cosine phi. And delta beta is equal to p sine theta sine phi. So let's now work to eliminate sine phi. So let's go back to the spherical triangle. Have the triangle KXX. So this angle is the longitude of the sun minus the longitude of the star. This angle here is 90 plus phi. And the sides, this is 90. And this is theta, which was the angle from the star to the sun. So we can apply the law of sines here. That's sine of 90 plus psi over sine of 90, or 1, is equal to sine of lambda of the sun minus lambda over sine of theta. So this is, of course, 1. And your relationship is cosine phi sine theta is equal to sine of lambda s minus lambda. Now we can apply also the law of cosines, the fundamental law of cosines to this triangle. So this side here, kx, is 90 minus beta. And if you apply to this angle here, 90, you have cosine of 90, which is 0, is equal to cosine theta, cosine 90 minus beta, plus sine theta, sine 90 minus beta, cosine 90 plus phi. Now, if we solve for the cosine 90 plus minus and sine plus minus, that yields sine theta sine phi is equal to cosine theta sine beta cosine phi, cosine beta. Now, if we apply the law of cosines again to obtain the cosine of theta, cosine of theta is equal to cosine of 90 times cosine of 90 minus beta plus sine of 90 sine 90 minus beta times cosine of lambda sine minus lambda. So sine of 90 is of course 1 and cosine of 90 is 0. So this reduces to cosine theta is equal to cosine beta times cosine lambda s minus lambda. So we have these three equations called equation 1, equation 2, and equation 3. Now we can substitute equation 3 into equation 2 to eliminate cosine beta. Cosine theta here eliminates on both sides. You find that then sine theta sine phi is equal to sine beta cosine of lambda sine minus lambda. So look, we wanted to find delta lambda and delta beta. For delta lambda, we want sine theta cosine psi, which is what you have in equation 1. And for delta beta, you want to find sine theta sine psi, which is what you have in equation 4. So you can substitute these equations and find delta lambda cosine beta is equal to p sine lambda s minus lambda, and delta beta is equal to p times sine beta cosine lambda s minus lambda. Now, since these are sines and cosines of the same angle, you can square them. You have delta lambda cosine beta over p squared is equal to sine squared of lambda s minus lambda. And delta beta squared over p squared sine beta squared is equal to cosine squared of lambda s minus lambda. Since these are sine and cosine of the same angle, if you sum them, they must be equal to 1. This is an equation of the form x squared over a squared plus y squared over b squared is equal to 1, which is an ellipse. The parameters are x equal to delta lambda cosine beta, y is equal to delta beta, and a, the semi-major axis, is equal to the parallax shift, and b, the semi-minor axis, is equal to parallax shift times the sine of beta, which is why, if the star is in the ecliptic, then you have sine beta goes 0, and it degenerates into a line. And at the pole, sine beta is equal to 1, but for generic ecliptic latitude, the star is going to trace an ellipse.